A very good morning and welcome back to the course of microengineering. In today's lecture, we will move ahead with the another type of linear beam tube which is used in microwave application. So if you recall, last time we discussed in detail the working principle of a two cavity klystron tube as an amplifier, right? And in the previous lectures also we have derived the mathematical derivation for the velocity modulation equations, as well as we saw the bunching factor, and we have calculated what should be the distance of the bunching in order to took place in an effective manner. And we have established a relationship between the optimum distance in the drift space with respect to the distance at which the bunches are formed in the two cavity klystron amplifier. Okay, so the two cavity klystron amplifier, though it is being used as a microwave amplifier, sometimes the gain provided by two cavity klystron amplifier is not sufficient. So at that time what we can do is we can add more number of cavities to the existing structure of two cavity klystron, and the structure will become multi cavity klystron, right? So we will discuss a multi cavity klystron in a brief, and then we will go for the detailed inspection of the next type of tube, that is a reflex klystron. Practically, the multi-cavity klystron and two-cavity klystron both are amplifiers. Only the thing is, if the gain provided by two-cavity klystron amplifier is not sufficient, then one can go for utilizing the multi-cavity klystron, in which the gain overall of the amplification process we will get much more larger, and as per the expectation of the standards. So let us devote some time in order to see the constructional difference of multi-cavity klystron when it is compared to two-cavity klystron. So here I will start multi-cavity klystron. There is only difference in the construction, rest the velocity modulation process is same as we saw in the case of a two cavity klystron. Only the difference is that here we are going to make use of multiple cavities. So that's why it is called as a multi cavity klystron. And again it is used as a amplifier. When the gain provided by two cavity klystron amplifier is not sufficient, then one can go for using this multi cavity klystron circuit. Okay, so how this will look like, I will embed the image. Okay, so this is the image of multi cavity klystron. So here I will explain you one by one the construction. So here what we observe, I will change the color. The electron gun is same over here. This is the electron gun. Now this electron gun is supplied with a negative bias as usual. Only here the thing is that instead of using two separate cavities, we can make use of multiple cavities. So here if you see, cavity number 1, cavity number 2, cavity number 3 and cavity number 4. So here the cavities are 1, 2, 3 and 4. These are resonant cavities. These are resonant cavities. So in the case of two cavity klystron, we already know that it consists of two cavities. But if we have more than two number of cavities, we can call the same configuration as a multi cavity klystron. Rest of the arrangement, there is a small change in the arrangement of multi cavity klystron. So here we are using these solenoids over here. Okay, so these solenoids are used in order to focus the electron beam exactly at the center, so that maximum interaction of the microwave signal will take place with the electron beam in order to extract maximum amount of energy from the electrons, right? So the bunching process and the velocity modulation, these are interrelated with each other. Okay, So we already know the term velocity modulation, in which the speed of the electron will get varied by means of presence of the microwave signal, right? So here the only difference is that the amount of amplification that we are going to get when we take the signal out from the last cavity over here is that it will be sufficiently amplified, and the gain which we achieve, that is much more larger compared to the gain provided by two cavity klystron, right? So construction wise there is no as such a difference, but the only thing is that we are going to include more number of cavities in the same structure, and that's why this circuit will become multi cavity klystron, and essentially it acts as an amplifier circuit, right? So construction wise there is no difference, only the thing is that we are going to include more number of cavities. So more number of cavities means there will take place more interaction between the electrons and the micro signal which we want to. So this interaction is continuously taking place, and continuously a process of bunching is taking place over here. Now here you may ask me, where is the drift space that we need to consider? Always remember that the drift space is always calculated from the first cavity. So here it is the first cavity and the last cavity is over here. Okay. So in this particular case, for multi-cavity klystron, the drift space is much more longer. So this is a drift space, this I denote with letter capital L. So in a two cavity klystron amplifier, whatever drift space we have, that is very small. Okay. So as we include more number of cavities, the drift space is the spacing between the first cavity and the last cavity. And definitely as the drift space is more in the case of multi cavity klystron, more the drift space, what it will give, if drift space is large, or it is more, it will give more interaction, right, between electrons and signal. As there will take place large amount of interaction between the signal and electrons, the more bunches are going to form, and these bunches are adjusted such that when they arrive at the last cavity, during that one the phase of the micro signal we will adjust negative going, such that the maximum formed bunches will give up the energy to the micro signal, and thus the micro signal appears largely amplified at the output of last cavity. Okay. So in the case of a working, there is no as such a difference, only here we are going to include more number of cavities, and multi cavity klystron is only used when the gain provided by two cavity klystron amplifier, that is not sufficient. So at that time one can make use of this configuration, right, and by using this configuration the gain can be increased further, whatever it is given in comparison with the two cavity klystron amplifier. Okay. So we will go ahead and let us start inspecting the next linear beam tube, that is a reflex klystron. So now we will start with the reflex klystron theory. Reflex klystron is essentially used as an oscillator. Reflex klystron is a tube. Okay. It is basically used as an oscillator circuit. Okay. So let us see construction wise how the reflex klystron look like. I will insert the diagram. So here the reflex klystron, I would like to include the diagram. So this is the construction diagram of reflex klystron, how it look like. Okay. So if you clearly visualize, all the things are clearly represented over here. we have a cathode over here on the left hand side, starting with. So this cathode is supplied with a sufficient negative potential over here. Okay, so normally this potential is a DC potential and we denote it with V0 basically, right? So this DC voltage is applied to the cathode so that the cathode will get heated up and it will generate a source of electron in the form of a beam. Now the next element which is placed in front of a cathode is the anode. Now the anode is actually connected to the positive potential. So in order to attract the electrons released by the cathode over here. So when the cathode will release electrons in this way, they will get attracted towards the anode because the anode is relatively placed at a positive potential and it is grounded. Okay, so that the electrons will get attracted. When the electron beam passes over the first cavity, now here you observe that this is a single cavity. The Reflex Klystron makes use of single cavity for their operation. Okay, and this particular tube is essentially used as an oscillator rather than amplifier. Now this single cavity has a small narrow width, or we call it as a cavity gap. So this is a cavity gap. So D is nothing but a cavity gap. Only single cavity is used with a small cavity gap denoted with small letter d. Okay, and here if you observe, initially we are connecting a source of a microwave with the amplitude Vs to the cavity. So this initial triggering source of the signal is necessary in order to set up the oscillation in this single cavity. Okay, once the oscillations are built up into this particular cavity, the source of a microwave we can remove and the cavity will continue to go resonating and it will continuously generate the microwave signal, right? So there is one more potential here which plays a very important role, and the overall operation of the Reflex Klystron as an oscillator depends upon this particular DC voltage. Now this DC voltage we call it as a repeller voltage, and sometimes it is also called as a reflector voltage. So VR is the repeller voltage, please remember. Repeller voltage, or it is also known as a reflector voltage. Okay, and finally if you see over here on the right hand side we have that reflector. It is not a collector plate, remember, it is a repeller. So this repeller is connected with a negative large potential. Please remember, this repeller is not collector. In the case of a 2-cavity klystron amplifier, the last terminal was the collector which is connected to the positive potential. But here please remember, we are using the repeller electrode which is connected to the negative potential. Now what is the principle of operation of working? So here in brief I will explain you. When the cathode gets heated up, it will start emitting beam of electron. This beam of electron will get accelerated towards the cavity by making use of the anode, which is relatively kept at a high potential compared to the charge on electrons, so that it will attract the electrons when the electron beam reaches at the cavity, right? So in the cavity, initially we are going to set up certain microwave signal. Okay, so this microwave signal has an amplitude Vs. The amplitude of this microwave signal we will maintain very small, right? So initially we need to place a small microwave signal in the cavity. So when the electrons reaches at the cavity over here, right, so they will influence this microwave signal. Okay, and the electrons then leave the cavity and they will start going towards the repeller, right? So here we already know that the repeller is negatively charged. It is connected to strong negative voltage. When the electron tries to come near to the repeller, due to negative potential of the repeller, they will get bent back, so they will get repelled. and the path of the electron will be reversed in this way, right? So the same is shown over here. Initially the electron will pass in a straight way. When they come closer to the repeller, they will get reverted back and they are repelled back again towards the cavity. So the electrons initially, say suppose over here I will denote, this is say a cavity gap. Okay, so this cavity gap is small d, right? Now this cavity gap we call it as a small d, starting with a 0 distance to distance d. Okay, let us say the electrons are going to enter at time t0, the small cavity gap, and the electrons are going to leave the cavity at time say t1. So t0 is the time during which the electrons enter the cavity of small width d, and at time t1 the electrons will leave the cavity, right? And they, when they leave, over here we have the repeller plate in this way. The repeller plate is already connected with a negative potential, so when the electron pass in this way and when they come closer to repeller, they will get repelled back in this way. Okay, and when they get repelled back, the electrons which got repelled back by the repeller, they will come back again to the cavity at time say t2. So please remember, time t1 is the time at which the electrons are going to leave the cavity, and time t2 is the time at which the repelled electrons are again going to enter the cavity, right? So here please remember, the electron when get repelled back by the repeller, they will again enter into the cavity. Okay, so due to this repelling, the total electrons will travel the twice of the distance which is formed by the cavity, right? So here the forward signal or the forward electrons which are coming in this direction and the repelled electrons which are coming in the opposite direction, they will start resonating inside this particular cavity. Okay, so the forward going electrons and the reverse coming electrons which are repelled back by the repeller, both of these electrons are going to set up certain oscillation inside this particular cavity. Okay, and these oscillations, because of the forward traveling bunches of electron and repelled electrons, they will interact with each other and they will set up the oscillation in the cavity. And when we take out that oscillation from the cavity, we will see that it is a very high frequency signal. The oscillations are very high, and these oscillations are then utilized as a microwave signal, right? So this particular reflex klystron is essentially used as an oscillator circuit rather than amplifier circuit. Only the thing over here is that the reflex klystron is utilized at a very low power level, and the typical application which makes use of reflex klystron as a oscillator circuit are include the laboratory based microwave generators. Okay, so we are having a couple of experiment on the reflex klystron characteristic. So there at that time we will see how this particular reflex klystron practically works. Okay, so the best example where we use this reflex klystron is low power microwave link. Okay, because the power output exhibited by this microwave signal is very less, and this makes it useful in order to be utilized in the laboratory experimentation and in certain low powered microwave link communication. So this is the simple operation of the reflex klystron. Remember that reflex klystron simply utilizes a single cavity, and initial oscillation in the cavity we need to set by momentarily applying the microwave signal. Once the bunches are formed by the forward traveling electrons and the repelled electrons, these will start interacting in the cavity, and these electrons are then going to set up the self-contained oscillation in the cavity. At that time, this particular microwave source we can remove from the circuit, and the circuit will continuously act as a sustained oscillator which will generate a very high frequency, and this can be used as a source of a microwave signal at a low power. Okay, so this is the simple operation how the reflex klystron tube works as the source of a microwave signal, or it is an oscillator, right? So here again, as this reflex klystron is dependent on the bunching process. As we saw the bunching process in the case of a two cavity klystron, the working principle of this reflex klystron is also dependent on the bunching factor. Okay, so the way in which we derived the mathematical equation for the bunching factor and the transit angle of the two cavity klystron, so here also we will have that short derivation, and through this derivation we will evaluate a mathematical equation for the bunching factor in the reflex klystron. So let us go ahead with that. So here I will give the title as derivation of bunching factor and transit angle for reflex klystron. Okay, so before going to the derivation, let me elaborate you the same velocity time diagram for the reflex klystron. This is essentially same as that of the velocity time diagram that we saw in the case of two cavity klystron, right? So the velocity time diagram for the two cavity klystron, I will insert that. Okay, so here I will briefly illustrate you how this particular velocity time diagram happens for the reflex klystron. So here, let us say here I will denote with a red color. So the signal which is sinusoidally varying, right? This particular signal. This is our microwave signal. Okay. So this is our microwave signal. This microwave signal has certain time period. Now this microwave signal we are applying over here at the cavity, if you recall, that is this signal. Okay, so this microwave signal is required in order to start the velocity modulation process in that single cavity. Okay, so here we consider three different cases at which the electrons are going to behave differently with their velocities, right? So first consider that the microwave signal is going through its zero phase. Now let us denote that position as number 1. So at point number 1, the microwave signal, if you observe, is essentially 0. Okay. At point number 2 over here, I will denote this as a point number 2. At point number 2, microwave signal has its maximum peak. Right? It is maximum. And there is another moment here. Let us call this as a point number 3. At point number 3, we see that the microwave signal is minimum, or it is a negative peak. Minimum or negative. Okay. So what happens because of this type of a behavior of the microwave signal that we are applying momentarily at the input of single cavity in reflex klystron? So because of this, whatever electrons are entering, the electrons will get their velocities differentially modulated. Okay, so here if we take the example of the first case where the microwave signal is 0, so at that time the velocity of the electrons remain unchanged, and the electrons will travel through the cavity gap in this way. So this particular one is no change electrons, no change velocity, no change velocity, the middle one, which is I denoted with a red color. Okay, so similarly what happens when the electrons enter the cavity gap small d during the positive going of the microwave signal when it is maximum? I will denote with some different color. Let us say with this blue color I will denote. So at point number 2, the electrons will get accelerated. As electrons will get accelerated more, they will travel greater distance in the cavity. Okay, so this second blue color indicates accelerated velocity of electron. Accelerated velocity I will denote. And similarly, when the microwave signal is going through its negative peak, at that time the electrons will get retarded, right? And at that time the electron will travel lesser distance in the cavity, which I denote with this green color now, in this way. Okay, so this green color indicates deaccelerated electrons or deaccelerated velocity, you can write. So what happens then? So this process will continuously take place. Acceleration of the electrons, deacceleration of the electrons, and no change in the velocity of electrons. So this will continue, and if you consider the reference electron over here, okay, so I will choose this color now. Now let us say we will choose a reference electron where the microwave signal is going through its 0 amplitude. So from the reference electron position, that is at position number 1, all these different types of electrons, that is the electrons which got speeded up, the electrons which has constant velocity, and the electrons which has slower velocity, all these electrons are going to come and they are going to form bunches over here sometime in the time. So when we take the reference time period when the microwave signal is going through 0, all these electrons are going to combine with each other. They are supposed to meet with each other and form a bunch. Okay, so this is that typical duration over here. So I will denote here bunched position of all electrons. Okay, all these 3 different types of electrons, they are going to meet with each other at certain time. Now that time with respect to the reference of the micro signal when it is going through 0, if you see, so somewhere here, okay, this is that particular time at which the bunching is taking place when it is compared with respect to reference position of the micro signal when it is going through 0. So the reference position is 1. So if you count the total number of cycle in this particular time period, so here from here to here, so I will denote from start to this particular point, it is 1 cycle. Okay, this is 1 cycle, and here from here to here you will get 3/4 cycle. Okay, so the total time period over here is 1 complete cycle plus 3/4 cycle. Okay, so this is the time period. Okay, so the time period where the bunching of all the different types of electron will take place is, we are going to get 1 and 3/4 cycle. Okay, so this we call it as a fundamental operating mode of the reflex klystron. Okay, so at 3/4 we can say over here it is at a 3/4, and when we add one more cycle we will get 1 and 3/4, and likewise. So 3/4 and 1 and 3/4 are the basic fundamental operating mode of the reflex klystron, where we will get maximum bunching, and at that time we will extract maximum energy from these electrons, and the sustained oscillation from the reflex klystron we are going to obtain. Okay, so this particular diagram clearly demonstrates how the bunching is taking place at a specific time interval in the case of reflex klystron. And here we found that the bunching is taking place, especially a larger amount with large power, at the cycle 1 and 3/4 of the microsignal. Bunching is also taking place at a smaller distance, that is at a 3/4, but please remember that at 3/4 cycle of the microsignal, the bunching will not provide us the maximum amount of energy, right? So normally 1 and 3/4 cycle we are utilizing as a fundamental operating mode of the reflex klystron tube, right? So in the derivation, this part will be clear to you in a more detail. So let us go ahead and derive the derivation or the expression for the bunching factor and transit angle when we operate our reflex klystron. So let us go ahead. Now, again we begin with the fundamental initial velocity of the electrons. So velocity of electrons, we know how the velocity of electrons is given when it is released by the cathode. Velocity of electrons, we will denote that with small letter v0. How it is given? It is dependent upon 2e v0 by small m square root, right? So where E is the charge on the electron, and where m, small m, is the mass on the electron, and capital V0 is the DC voltage. Okay, so when we substitute the value of electron charge to mass, okay, so we will get this equation approximately as 0.593 square root of V0, right, into 10 raised to 6 meter per second approximately. Okay, so when you substitute the charge on the electron and the mass of the electron, approximately you will get this particular equation. Now next is when the electron leave the cavity. Now here we have the single cavity, and what is the spacing of this cavity? The spacing of this cavity is d, right? So when the electron leave this cavity, that means the electrons are going to travel a distance small d. Now they leave the cavity at time t1 over here. When they leave the electron, when they leave the cavity of this reflex klystron, that will take place at time t1. Okay, so we want to write what is the velocity of these electron when they leave this particular cavity. Okay, so here I will write when electrons leave the cavity of width d at time t1, right? T1 we saw over here. Here we have drawn that diagram, and this is that time at which they will come out of that cavity of spacing d. At time t1, the velocity of electrons given by, now how that can be given by, you can recall the velocity modulation equation, the standard equation of velocity modulation. So we can write the time at which the electrons are leaving is a t1, and the velocity of electrons at this particular time is v of t1. This can be written as a original velocity v0 into bracket directly from the velocity modulation equation, 1 plus beta I v1 upon 2v0, right, sine of omega t1 minus theta g by 2. Bracket complete. Equation number 2. Okay, so where v0 is initial velocity, which is given by equation number 1, beta I is the beam coupling coefficient, we know that this beam coupling coefficient will get maximum value 1 when 100% coupling is take place. What is V1? V1 is magnitude of micro signal, right, which we are going to set up momentarily in order to initiate the operation of a oscillation for the reflex klystron. And what is capital V0? V0 is a DC electric field which we apply to the cathode in order to generate electrons. Okay, so this is the velocity equation of electrons when the electrons are going to leave the single cavity of width d. Okay, so next we see when the electron approach to the repeller over here. So when the electron leave this particular cavity with velocity v of t1 here, they will start approaching towards the repeller. Okay, so when they start approaching to the repeller, as we already know that the repeller is connected to negative potential, so what will happen? The repeller will push back these electrons back towards the cavity, so that the electrons, when they reach closer to the repeller, they will get reverted back and they will be pushed again towards the cavity gap. So here I will write that statement. When electrons, I will write over here, when electrons approach repeller, they will get retarded, or rather we'll write they will get repelled. Repelled means they will get pushed back. They will get repelled by repeller voltage. Okay, so this repeller voltage we call it as a VR. That is again a DC voltage, right? So the electric field, so the total electric field, therefore electric field, how it is given? Electric field E is equal to total electric field, so that becomes sum of the repeller voltage, that is VR, plus the DC field which we applied to the cathode V0, plus the micro signal with amplitude V1 sine omega t. Okay, and whole thing divided by the drift space L. Okay, so where L, we can say this is an equation number 3. And what is L? L is a drift space, please remember. Remember, drift space is a different and cavity gap is a different. So where is the drift space? Where we denote the drift space? This is a particular drift space here, that is L. And if you want to indicate where is the drift space, so here if you see this particular blue diagram, blue line that I am drawing, that is nothing but the repeller or the drift space. Okay, so that is capital L. So the total electric field is given by VR plus V0 plus V1 sine omega t divided by capital L. Okay, so what will happen when the repeller is going to push back these electrons back towards the cavity? The repelled electron will come back at the cavity at other time, which is given by T2. Okay, so when they will get reverse back in this way, they will again come at T2 in order to enter the cavity back. So here I will write that statement. Repelled electrons return back to the same cavity of width small d at time t2. At time t2, and they will exert a force. Now this force can be given as, from the basic law of mechanics, force is equal to mass into acceleration. Okay, so this can be written as minus E into E. This is a well-known equation. Let us call this an equation number 4. Right? So here I can write this force exerted by electron F is equal to mass into acceleration. We know acceleration is the derivative of the velocity, and the velocity is again the derivative of the distance. Okay, so here let's say distance covered by electrons is, say, small z. Okay, so if z is the distance covered by electrons, then dz by dt indicates velocity. Okay, and if I take double derivative d by dt of dz by dt, so this what then represents d2z upon dt square, and this particular term represents acceleration. Okay, so here the acceleration term over here I can replace with a term d2z upon dt square. Okay, and this I will equate to minus E into E. Okay, now substitute equation 3 in above equation. So if I substitute equation number 3, that is the electric field total, in above equation, so I can write force is equal to mass into acceleration. The acceleration I replace with d2z upon dt square, which is given by minus E into capital E. Now this capital E I replace with equation number 3, VR plus V0 plus V1 sine omega t divided by L. Okay, let us call this an equation number 5. Right? So here now we see the voltage amplitude. Now as repeller voltage and the DC voltage, if you add them together, this quantity will become very much greater than the magnitude of momentarily microwave signal that we are introducing. Okay, so this relation holds true because when we add the repeller voltage with the applied DC voltage, the magnitude is very much higher when it is compared to the magnitude of the microwave signal. So what we can do is we can neglect microwave signal. In equation 5. So as we know, the magnitude of repeller voltage and DC voltage is very much higher compared to magnitude of micro signal we can neglect the microwave signal and we can rewrite the same equation as f is equal to m d2z upon dt square as it is. Now I will neglect the micro signal and I will keep the remaining things, Vr plus V0 divided by L. So I can write like this. Okay, so here what we can write, so this can be written as m d2z upon dt square, which can be written as minus e into bracket Vr plus V0 divided by L. Okay, so let us call this as an equation number 6. Okay, now what we can do is we can take this mass of the electron on the right hand side. On the left hand side we get therefore d2z upon dt square. I will take the mass of the electron on the right hand side, so this can be written as minus e by m, right, into bracket repeller voltage plus DC voltage divided by capital L. Right, now integrating this equation, I'll write integrating this equation on both sides. So if I integrate this particular equation on both sides, I will get dz by dt when I integrate on both sides, right, minus e by m, L is again constant 1 by L, and Vr, V0 are again constant because these are the voltages from time t1 to t dt. Okay, so when we integrate on the right hand side. Okay, so what we get from this I can write dz by dt, right, is equal to minus e into bracket Vr plus V0 divided by m into capital L. Okay, t minus t1, when I solve the integration, t minus t1 plus some constant of integration I will get, that is c1. Okay, so let us call this an equation number 7. So when I integrate equation number 6, I will get equation number 7 with certain constant c1. Now we want to evaluate what is that constant c1. Okay, so this constant c1 can be calculated by placing t is equal to t1. So here I will write, now put t is equal to t1 in equation 7 to evaluate constant c1. In order to evaluate the constant c1, what I will do is in equation number 7 I will put t is equal to t1. Okay, so at t is equal to t1 I will rewrite dz by dt is equal to minus e Vr plus V0 divided by m into L. Now at t is equal to t1, this term will become 0 plus c1, right? So this will give me c1, that is a constant, equal to dz by dt. And what is dz by dt? Z is a distance and dz by dt is the velocity, right? So this velocity is when electrons are leaving the cavity, v of t1. Okay, so let us call this an equation number 8 for the constant. Okay, so substitute constant c1 from equation 8 into equation 7. So what we do is we will place the value of that constant which we got in equation number 8 back into equation 7. So what we will get then? We will get the equation dz by dt, equation 7, minus e vr plus v0 divided by ml. Right, now here the t minus t1 as it is, and this constant we have got is equal to velocity v of t1. Okay, so let us call this an equation number 9 now. Okay, now what we do is, now again we integrate. Now we again integrate on both sides. Of equation 9. Okay, so we integrate both sides of equation number 9. So what we'll get then? So when we integrate on the left hand side, I will get z is equal to, right, minus e vr plus v0 divided by m into l, right, as it is. Now here I will get the integration from t1 to t minus t1. Okay, and velocity v of t1 is a constant. I will take it out again from t1 to t of dt, right. So when we solve this particular integration equation, we get z is equal to, that is distance z is a distance. How this can be written then? Minus e into bracket vr plus v0 divided by ml. Okay, so when you simplify this, the term you will get t minus t1 whole square plus v of t1, velocity of electrons at time t1, into t minus t1 plus constant of integration c2. Let us call this an equation number 10. Right, now we need to find this constant from equation number 10. So what we do is put t is equal to t1, put t is equal to t1. So at t is equal to t1, z is nothing but the cavity gap, right. So this is how, see over here, at t is equal to t1, refer to this particular diagram. At time t is equal to t1, the distance has covered is equal to small d. Okay, so the distance z will become small d at t is equal to t1. You substitute. So at t is equal to t1, z will become small d. Okay, so minus e vr plus v0. Substitute in equation number 10 in order to calculate the constant of integration, that is c2, divided by ml. Now when I substitute t is equal to t1 over here, this term will become 0 plus velocity at t1. At t is equal to t1, this term will become 0 plus c2. So what we get from this? The constant of integration from this, we will get c2 is equal to d. Let us call this an equation number 11. So we have found out the constant of integration in this equation. Okay, so we substitute, I'll write here, substituting constant value c2 in equation 10. So when you substitute this value of constant c2 in equation 10, what we get? Z is equal to, that is a distance in general. So you substitute C2 value over here. How that can be written? It can be written as minus E VR plus V0 divided by M into L, right? T minus T1 square plus velocity at T1 into T minus T1, and what is the value of constant C2? That is D. Substituting. Okay, so let us call this an equation number 12, right? So next, as electrons return back, see here over the diagram which I drawn on the right hand side, at what time the electrons will get return back to the cavity? When it get repelled by the repeller at time t2. Okay, so here I write, as electron return to the cavity at time t2, they will return back to the cavity at time t2, right? So here this particular time I will denote t is equal to t2. Okay, at that time the z is equal to again d, right? So here I will replace the z is equal to d, right, minus E VR plus V0 divided by M into L. Now here in the place of t I will replace as a t2 minus t1 whole square plus velocity at t1, right, into t is replaced with a t2 minus t1 plus d. Okay, so here we see that this equation we can now simplify further. So the d on the both side will get cancelled. So what we can write directly, the time gap t2 minus t1, we can write this is equal to 2m into capital L into velocity v of t1 divided by E VR plus V0. Okay, now here this particular difference of the time we call it as a t dash, and this difference of the time denotes the round trip transit time of electron in reflex klystron. So call this an equation number 13. So t dash is nothing but the time difference t2 minus t1, and this represents round trip transit time in the reflex klystron operation. Okay, now next we know from velocity modulation process what we know from the velocity modulation process, how the velocity of electron at time t1 is given. So that is v of t1 from velocity modulation equation. How we can write? Original velocity v0 into bracket we have 1 plus beta I v1 upon 2 v0, right, sine of omega t1 minus theta g by 2 from the theory of velocity modulation. Therefore transit time t dash, now here you can replace 2ml, right, divided by E times VR plus V0. Now this V of T1 term you can replace with this particular term. So this can be written as V0 into bracket 1 plus beta I V1 upon 2 V0 sine of omega T1 minus theta g by 2. Okay. Now here this particular term that I will highlight. So this term over here I can write T dash is equal to T0 dash. So this particular I will consider it as a T0 dash. T0 dash into I can write 1 plus beta I V1 upon 2V0 into sine of omega T1 minus theta g divided by 2 as it is. Okay, so let us call this an equation number. Let us call this as an equation number 14 first. Okay, and let us call this as an equation number 15, where T0 dash we call it as a DC round trip transit time. DC round trip transit time in Reflex Klystron, and this is given by T0 dash DC round trip transit time is given by 2 ml original velocity V0 divided by E times VR plus V0. Okay, so let us call this an equation number 16, right? So here what we do is multiply equation 15 on both sides by omega. So here I will write multiply equation 15 both sides by term omega. Okay, so what we'll get omega t dash is equal to, right, omega t0 dash into bracket 1 plus beta I v1 upon 2v0, right, into sine omega t1 minus theta g by 2, bracket complete. Okay, so here omega t dash can be also expressed as, so here this can be written as omega t2 minus t1, right? So here omega t dash can be written as theta 0 dash plus x dash sine of omega t1 minus theta g divided by 2. Okay, so let us call this an equation number 17, where this particular term, which one? The first term. Okay, where theta 0 dash is nothing but omega t0 dash. Okay, and this indicates round trip DC angle, round trip DC angle of electron bunch. Okay, so theta 0 dash indicates round trip DC angle of bunch of the electrons. Okay, and what is x dash? So x dash over here, this represents bunching factor for Reflex Klystron. So x dash is bunching factor of Reflex Klystron tube. And how it is given? This is given as beta I v1 upon 2v0 theta 0 dash. Okay, so this is an equation number 18. So here equation number 18 indicates the mathematical equation for the bunching factor that take place in the operation of Reflex Klystron whenever it is used as an oscillator circuit. So this derivation is very clear to you. We started with the original velocity of electrons, and we took the help of velocity modulation equation. Then we wrote down the equation for the total electric field, and from that we established a equation for the force exerted by the repelled electron back on the cavity, and from that we have calculated the distance, and by evaluating the different constant in the equation, finally we successfully implemented the mathematical equation for the round trip transit time of the electrons in the operation of reflex klystron. And also we have calculated and we have developed the equation for the bunching factor that the reflex klystron is going to get operated on. Okay, so this particular derivation, I hope it is clear, and in this derivation we derived successfully the bunching factor of the reflex klystron and the DC transit angle of the bunched electrons. So as the name itself indicates, derivation of the bunching factor and transit angle for the reflex klystron. Okay, and before that I have explained you in detail the working principle of the reflex klystron and the associated Applegate diagram for reflex klystron, right? So here this particular thing is very important because the bunching at which the distance we are going to keep, that is very critical, and normally this particular time we take it as 1 3/4 cycle. The thing will become more clear to you when we typically solve the example based on the reflex klystron, where we will see how the fundamental operating mode of the reflex klystron we need to take at bunching center, which is taking place at 1 3/4 cycle, right? So what we do is, in the next lecture we will go ahead with the next type of linear beam tube, that is a traveling wave tube. Okay, so I hope you understood the whole working principle of the reflex klystron and the associated derivation. As I already told, the reflex klystron is popularly used as a low power microwave signal generator in the laboratory, as well as it is used in certain low power microwave links, right? So efficiency of this particular device is very less because it includes the noisy operation of the oscillation process. So the efficiency wise it will be around 30 to 40%, and it is a low power device. Okay, so this particular reflex klystron is popularly utilized in laboratory usage in order to generate the microwave signal. Okay, so we will stop here, and from the next lecture we will start again with the new type of linear beam tube, that is traveling wave tube, which is actually acting as an amplifying device. So we'll stop here, and thank you very much.